Okay, I think we can start. Welcome to the second day of Open Source Days. We're happy to be here with you today, and we're from Intel. We're going to be sharing with you the open source Intel OneAPI Rendering Toolkit. Just a little bit about who we are. There's going to be a number of speakers today. We're part of the Advanced Rendering and Visualization Architecture Group, or ARVA, inside of Intel. We're responsible for a number of products, all fully open sourced, some of which this audience may be already familiar with, and other ones that today we're going to present are a bit newer. We're known for the Embry, Open Image Denoise, OpenVKL, Osprey, OpenSWR, and Anari, in part with a number of other partners in the Khronos Group. Once again, like I said, we're fully open sourced, every project we work on. Just quickly, we're going to do a quick update for Embry for people that may already be using Embry, and just updates over the last year. For people that, just a quick overview for Embry. Embry is essentially a bounding volume hierarchy that offers ray geometry intersections optimized for all the Intel instruction set architectures from SSE through AVX 512. Over the last year, we've added a number of new curve geometry types, such as Catmull ROM, round linear curves, cone curves. A new compact polys CMake option allows double index quad leaves, reduces memory. Added support for multi-level instancing. We've also added support for point queries, so closest point, nearest neighbors. Implemented a new min-width feature for curves and points, allows the tracker to increase the radius in a distance-dependent way. This is helpful for anti-aliasing techniques. Added quaternion motion blur. The RTC commit scene function can now get called during rendering for multiple threads to lazily build geometry. This improves on the previous implementation we had. Geometries can also now get attached to multiple scenes at the same time. And we've added collision detection support. So now Embry supports collision detection, broad-face collision detection for user geometries. And there's been numerous performance and robustness improvements. And coming very soon in the next release will be more encode and refilling builders for instance geometry. That's pretty much all we wanted to talk about with Embry today. If there are questions, though, feel free to ask any questions on Embry. We can get them to the end. We want to concentrate on a number of other projects that we do. First will be Attila Afra with Open Image Denoise, and then Greg Johnson with OpenVKL, and then Jeff Amstutz with Anari. So I'll just hand it off to Attila for Open Image Denoise.
Thanks, Sean. So I will quickly introduce Open Image Denoise, a library for denoising for ray tracing. I will briefly go into some details how it works, how the API works as well, and what's planned for the future. So let's get started. Denoising nowadays is getting more and more popular because noise is pretty much inevitable in Monte Carlo ray tracing, path tracing solutions. So this means essentially that in many cases, rendering fully converged images is just too expensive. So the solution is basically rendering partially converged images and then denoising them with some kind of algorithm. The movie industry is also already using this approach where it's possible to get, it seems the slides are going forward without me clicking on them. Sorry about that. Okay, so it's possible to get 2 to 10x improvements with denoising without losing a significant amount of quality. And it's also actually crucial for real-time applications like games, where it's only possible to render only a few samples per pixel. So without denoising, the results would be just completely unusable. So the solution is to use some kind of denoising solution, and Intel Open Image Denoise is a denoising library which solves this problem. So this library is specifically targeted for ray tracing. It provides a set of high-quality deep learning-based denoising filters, and these filters are suitable for both interactive and offline rendering. And it's also possible to train the deep learning-based filters shipped with the library using the included training toolkit, which is based on PyTorch. I will mention this a bit later. The library runs on basically almost any modern CPU. The only requirement is having SSE 4.1, and it of course takes advantage of more advanced instruction sets up to AVX 512 as well. It runs on all three major popular platforms, Linux, Windows, and Mac OS. And the API was designed to be clean and minimal, so it can be integrated very easily into existing rendering solutions. In many cases, the integration could be completed in just a few hours. So let's see the denoising filters that the library contains. So the library contains currently two filters, all ray tracing oriented. One of them is a generic filter called RT, which aims for denoising generic path traced final frames. And there's also a dedicated light map denoising filter called RT light map, which provides higher quality for ray traced light maps. These filters, specifically the generic filter, accepts potentially multiple input buffers. Of course, there's the color buffer, which could be either HDR or LDR. And there are also ways to provide auxiliary feature buffers, which are completely optional. For example, it's possible to provide albedo and normal buffers, which can significantly improve the denoising quality. These buffers can be noisy as well, just like the color, so this doesn't have to be noise-free. So let's see the input and output buffers for the filters. So there's the color buffer and then the optional albedo and normal buffers. So here we can see an example for a scene rendered with path tracing, and providing these three input buffers where the color is the noisiest one, but the other two buffers are also noisy, just they're not really visible in this small size. Providing these buffers to the library will create the denoised image on the right. So basically this is how it works. Now, just to mention a little bit about the actual algorithm this is based on. So the algorithms in Open Image Denoise are based on deep learning approaches. Specifically, it uses a convolutional neural network, which has, in this case, a unit architecture. It provides a good balance between quality and performance. So it provides a quality that is suitable for final frame rendering, but also it's fast enough to use it in interactive applications on many core CPUs. Since this is a deep learning based filter, so it needs to have trained model as well for it, and the library ships with a set of pre-trained models, but it's not necessary to use them. Users can simply train these models with their own data sets, and these trained models can be specified through the API. So let's see a quick example of how Open Image Denoise works, what kind of results it can produce. So here we can see a frame from the Spring Blender Open movie. This was rendered with the cycles renderer at 32 samples per pixel. It's quite noisy, as we can see. Let's see what's the denoising output if we use albedo and normal buffers as well. So with this, we can achieve SSIM of 0.9. And just to see how the reference looks like, this is the ground truth. Let's see another example. So this image was rendered with the Khronos renderer at 16 samples per pixel. Let's see the denoised version, also using albedo and normal buffers as well. So this is the denoised version, SSIM of 0.91 roughly. And finally, this is the reference image. So that there is a difference, of course, but it's still an acceptable compromise in many cases, despite the fact that it's just 16 samples per pixel. Of course, the library works well with higher sample counts as well. It's just more visible in presentations like this to see lower sample counts. Just a quick mention about the performance, just to give you a rough idea of the ballpark performance that Open Image Denoise can achieve. On a 56 core machine with AVX 512 support, it's possible to denoise a 4K image in around 400 milliseconds, a full HD image in around 100 milliseconds, and a 720p image in around 50 to 60 milliseconds. So given enough cores, it's possible to use Open Image Denoise for interactive applications as well. I will just give a quick overview of the API. So the API is quite similar to the Embry API in design and philosophy. It has C and C++ versions as well, so it has a C++ wrapper included too. The API is object-oriented, and there are basically only three objects available in the API. There's a device object, similar to Embry, a buffer object, and a filter object. These are all reference counted, and this means that the library is quite compact and should be quite easy to use. So let's see a quick example how this works. The images can be denoised with these filter objects, and those can be created by first creating a device object. After the creation of the device object, we can just create a filter selecting what kind of filter we would like to use. In this case, we use the generic RT filter. Next, we have to set the filter parameters, which I will show in the next slide. We have to commit the changes before using the filter, and we just execute it. And then finally, we clean up. So this is the basic step. These are the basic steps needed to denoise an image. Let's see what happens in the filter setup. So the filter setup is also quite simple. Sorry. Oops. Okay, sorry about this. Okay, so first, either we need to use normal buffer objects or so-called shared buffers, where we don't create any buffer objects, just pass pointers that the application manages. Just like with Embry, we provide what type of buffer we specify, the color, albedo, normal, or the output itself. And we can also specify offsets and strides. So it's quite flexible, and different image layouts are possible. There is also a way to specify whether the image is HDR or LDR and some other parameters. So this is the basic idea of how to use the library. I would also like to mention the training toolkit, which was introduced quite recently to the library. The source code ships with a PyTorch-based neural network training toolkit, which consists of multiple Python-based scripts. With these, the users can train the filters with their own data sets, which has the advantage that it's possible to optimize the filters for custom renderers, sample counts, content types, or scenes. So it can potentially improve quality. And these user-trained filters can be either built into the library, or these can be loaded at runtime through the API. So there are multiple ways to use these customly trained filter models. Also, I would like to mention what is planned in the future for Open Image Denoise. So we're continuously improving the quality and performance as well. One of the next features that we'll introduce is directional light map denoising. So we have dedicated filters for not just regular light maps, but directional ones as well. For example, using spherical harmonic basis or some other basis. We're also working on adding temporal coherence, where denoising animations would result in much better temporal stability. And finally, we are also working on GPU support as well. The API is hardware agnostic, so basically adding a new type of device will not require changes on the application side, perhaps only just picking which device to use, which could be also using a default one. So it shouldn't cause any disruption in the applications. So as a conclusion, Intel Open Image Denoise is, as we've seen, an open source denoising library for ray tracing. It's suitable for both interactive and final frame rendering. It runs on all modern CPUs that support SSE 4.1. It has a simple, clean API. And you can download it from GitHub, and multiple resources are available at openimagedenoise.org, where you can find the detailed API documentation, example code, and a gallery as well for more example images. Thank you.
Okay, I am Greg Johnson. I will be presenting Intel Open Volume Kernel Library, or OpenVKL. So this is the newest component of Rendering Toolkit. So today I'll give a brief overview of OpenVKL, including describing its design goals. I'll talk in some detail about its supported volume types, as well as the APIs supported on those volume types, and then wrap up with resources where you could find additional information. So OpenVKL is part of Intel OneAPI Rendering Toolkit, which is an open source set of libraries for advanced rendering and visualization. In terms of a typical application software stack, OpenVKL sits at the same level as Embry as a low-level kernel library. So today, VKL is used extensively within Osprey, which is our scalable ray tracing-based rendering engine. And there it provides all of its volume functionality, enabling all of its volume rendering features. So OpenVKL can also be used within any renderer or any application to improve volume rendering features or performance. It has a SIMD-focused internal implementation with most kernels written in ISPC, and so we're able to take very good advantage of CPU vector instructions up through AVX 512. So Intel has announced the Intel Xe architecture GPUs, and so we won't talk in detail about that here, other than to say that OpenVKL and the other libraries shown here will support those libraries in the future. So what are the goals of OpenVKL? So put very briefly, OpenVKL intends to be an Embry-like library for volumes. And so as part of this, one of VKL's goals is to support a diverse set of volume types, just like Embry supports a diverse set of geometries. And so this enables applications and renderers to support many types of volumes through a single coherent API and generically written renderers. And so this allows applications to more easily make runtime decisions about which volume representation to use. And as we'll see, there are trade-offs between these different volume types. So it's important to allow applications to make those switches between volumes with minimal or no changes to application code. So OpenVKL does provide a flexible set of APIs primarily targeted at rendering applications. And so very specifically, authoring and volume manipulation workflows are out of scope for OpenVKL. We are really laser focused on supporting rendering applications in the APIs those need specifically. So we can talk about OpenVKL's features, both in terms of its supported volume types, as well as the APIs supported on those volumes. And so for volumes, we support many different representations ranging from dense structured in VDB sparse structured all the way through fully unstructured volumes and particle volumes. And then for APIs, we support volumetric sampling, gradient computation, ray-based interval iteration, which I'll talk more about, implicit isosurfacing or surface hit iteration, and volume observers, where I'll also show an example of that. So the first volume type is structured regular volumes. So here the domain is a regular grid, and the volume data is essentially a 3D array of dense voxels. And so this volume type provides extremely fast access, but does have a relatively large footprint in memory. And so this volume type is very good for fast rendering when data fits into memory. The next volume type is very similar. So the domain is in a regular grid, but but now on spherical coordinates, on radius, azimuth, and elevation. And so this has similar advantages and disadvantages to the previous volume type, but of course this volume is very well suited to problems with natively spherical structure. And so applications or simulations that use this volume type can pass it to VKL directly, and there's no need to transform the volume or resample it onto a less efficient volume type. So we then have adaptive mesh refinement volumes, or more specifically, block structured AMR. So we have some more flexibility here where we could provide data as nested structured regular grids. So these nested grids must fit neatly into their parent, but otherwise we're free to have as many levels of refinement as we want. And so a very flexible volume type. The traversal is somewhat more expensive. One important note is this is often used in large-scale scientific simulations. So again, can pass that volume type directly to VKL without needing to transform it. Another volume type we support is fully unstructured volumes. And so here we support arbitrary combinations of multiple cell types, so tetrahedra, hexahedra, wedges, and pyramid. And there's really no regular structure. And so we can place our cells wherever we want, really adapt to irregular forms, put our resolution and cell data where we need it. Because of this, no regular structure, traversal is moderately more expensive. So this is another volume type extensively used in large-scale simulations, finite element modeling, and so forth. And our newest volume type, which is somewhat different from the previous cell and voxel-based volumes, is our particle volumes. And so here a volume is made up of many individual particles, where each particle has its own position, weight, and radius of influence. And so when you sample a volume here at a point location, any number of particles are able to contribute to that sample value via Gaussian radial basis functions. So this volume type is used extensively in large-scale cosmological simulations, molecular dynamics, and other domains. And then last but not least, we have our VDB volumes. And so these are really pervasive throughout VFX and professional rendering. And so here the domain is a regular grid, and it supports sparse storage through nested regular grids where each level is a power of 2 in resolution. And so because of this regular structure, we have relatively fast traversal and fast access. And of course, a huge advantage is an efficient use of memory through this sparse representation. So some more detail on our VDB implementation. So VKL does have a compile time configurable topology for the different levels of the tree. And we do have a custom implementation for tree build and traversal. So this is implemented in ISBC, so we're able to do a full vector-wide build, traversal, sampling, and so forth to make that very fast. We support multiple reconstruction modes. So today that's nearest filtering and trilinear filtering. And then we have a hierarchical DDA implementation, which we use in interval iterators, which I'll talk about shortly. The animation you're seeing here is an example of VKL's volume observers. And so volume observers are a flexible component of the API that allow volumes to essentially communicate arbitrary metadata about their usage and statistics and so forth. And so in this example, the white parts of the cloud are inner nodes of the VDB tree. And through volume observers, we're able to communicate back to the application which regions of the volume where sampling is occurring, and then we're able to dynamically load leaf data on demand. And so this is a flexible mechanism for application side on-demand loading. So with our VDB support, we also ship a VDB utility library. So this integrates directly with OpenVDB and allows for very simple essentially one-line loading of VDB data sets. So one important point is that the leaf format that OpenVKL uses is completely compatible with OpenVDB. So you could pass those pointers directly to VKL, and through our shared buffer objects, VKL doesn't even need to make a copy of those. So memory efficient and zero copy. Today we are limited to scalar float fields, but that will likely change in the future. So OpenVKL supports many of these rendering-based APIs shown at the top. The API overall is a C99-based API, which is very similar to the other RenderKit components. We do provide ISPC bindings, and so if you're writing code in ISPC and using those uniform and varying constructs, you're able to also call directly into VKL. We do have multiple supported API modes for most of the APIs shown. And so taking sampling as an example, so we support scalar sampling, where you could sample a single point location at a time. We support vector-wide sampling, where you could sample 4, 8, or 16 locations at the same time, and under the hood, we'll make efficient use of SSE, AVX, AVX2, or AVX512 as appropriate. And then we also have stream-wide sampling, where we can sample arbitrary numbers of points at the same time. And under the hood, that will efficiently map to the most appropriate vector-wide interface. VKL does have fairly flexible data interfaces for providing data to it. So I already mentioned shared data buffers. We also support strided input data which can make it easier to work directly with data as it exists in application memory or maybe some custom structs. And then we have a module implementation that does support user extensions. And so if you had your own volume type you wanted to implement, that is possible within VKL. So one of the APIs I wanted to focus a little more in on is our array-based interval iteration, or interval iterators. And so this allows you to iterate over meaningful intervals along array. And what I mean by meaningful is that you are able to tell OpenVKL the volume values of interest through what we call a value selector object. And so that means that when you start iterating, let's see, we accidentally went forward a slide. So that means when you start iterating along array, you're able to skip any intervals that are known to not contain those values of interest. So that's a very efficient form of empty space skipping. And then the intervals you get back are not necessarily voxels. And so this is somewhat configurable per volume. And so as an example for VDB volumes, you could configure the depth of the VDB tree at which you intersect to find these intervals. And then finally, with the interval data, you do get back additional metadata. So one piece of information is the volume value range that you can encounter when sampling along that interval. And so this value min-max is useful for rendering methods such as delta tracking, where a very tight bound on volume adjoint can make your overall rendering much more efficient through requiring less sampling, for example. So that's the overview I wanted to give. There's more information available at openvkl.org, API documentation, tutorials in the code base, example renderers showing ways to integrate OpenVKL. We are part of RenderKit, so you could find information there. And then if you are attending SIGGRAPH, I encourage you to check out our demos. And so we have several demos coming from our group. One of these is a large-scale cloudscape interactive demo where you see images there on the right. So this makes heavy use of OpenVKL, Osprey, and Osprey Studio. And I believe those demos are going live on August 24th. Okay, thank you. And I will turn it over to Jeff Amstutz.
All right. And I have control, great. So I'm going to talk about Anari, which is a Khronos standard. So it's obviously not an Intel project. It's cross cross-vendor standard that's emerging. It has been it was at first in an exploratory group, and then middle of this year, we transitioned to a full working group working on a spec. So I'm going to just give a very brief overview of what it is and what we're working on, knowing that we just had a webinar yesterday that got on YouTube really quickly. So if you search Anari webinar, we have an entire hour-length presentation on it. So this is going to be condensed even from that. So hopefully this whets your appetite for what Anari is and what it isn't. So first, Anari is, it stands for the Analytic Rendering Interface. And the word analytic came from largely that the API that we're working on emerged from scientific visualization, but just know that what we're working on is not actually domain specific. So hopefully that the analytic part doesn't get too distracting from what we're working on. But the goal is to provide a commoditized interface to talk to a live software rendering system. And so all that means is a lot of us have data, we have file IO, scene graphs, applications that have their scene ready to go, but we there'll be an image to describe this later, but we have the problem of having to talk to everyone's custom API to translate that data from the application and share it with the renderer so the renderer can make an image of it. So Anari is seeking to commoditize specifying the what needs to be rendered and then how to get an image back, still letting the renderer define all of the why and the how that rendering gets done. So the illustration at the bottom is you have some input scene, you have some camera position, and you plumb that through Anari to let someone's renderer then make you an image that is desirable. So this emerged from scientific visualization, where there were a number of software packages like VTK and ParaView that every time there was a desire to use like a new ray tracing renderer that was shipped from a vendor such as Osprey, or there's VizRTX from NVIDIA. There's a number of great renderers out in the wild. Every single time that was desired to be brought into the software package, that you have to do an integration with that. Even though that level of translation to say, this is my application scene and I want you to make me a frame, that from the technical standpoint was largely still saying the same thing, that we had to spell it with different APIs over and over and over again. So to get to the lower level goods of what a renderer vendor might provide, we were trying to commoditize that to go from the left to then the right, where we have all of these packages talking to a single render API, and then let the vendors worry about the renderer, let the applications worry about their application. So more concretely, to put some names to this, this is the very high level stack of where Anari sits. And Anari is very thin. This is not trying to actually implement a lot, but instead standardize the way the top level applications talk to the lower level renderers. So we have some examples of renderers we've been working with in SciViz, Osprey, VizRTX, and then we've even had AMD participation in the working group with Radeon ProRender. But at the end of the day, you could substitute your renderer, commercial or open source. You could insert that there. That takes advantage of lower level APIs, like we've talked about Embry and OpenVKL. There's optics, all of these things to make a renderer, and then of course the hardware underneath it. But Anari is trying to not take on the entire scene graph problem, which deals with file IO, structural updates, metadata custom to a domain, all kinds of different concerns. We're trying to let that be domain specific, but once you boil down to want to render an image, that generally looks the same. That's what we're trying to commoditize. So succinctly, this ends up being a viewport rendering API. So not a scene graph. There's so much both application specific, domain specific libraries and tools out there that exist, and standardizing on all of those is really ambitious and difficult. So we're trying to make sure that what remains in scope is going to actually serve us to benefit, to basically manage expectations is what that boils down to for Anari. And then also to help with this, to maintain that separation is our goal is to remain maximally unidirectional. And all that means is all that structure, data arrays, where parameters come from, where they're queried remains in the application, and you share it with Anari. Anari is not trying to be a framework to go build all of those things. Instead, it's how do you share that information with a renderer? So this gives us lots of freedom to do interesting things as renderer implementers, to be divorced from all of that complexity while still dealing with the complexity we have by implementing renderers. And one cool example of this, there's a ton of possibilities there of what freedom helps us with as implementers of rendering systems, but just diverse execution topologies is one that is a big deal in SciViz and one we're taking very seriously with Anari. I think most of us probably think when we want to render something, we think of the left-hand side. We have a single application running on a single machine talking to an API that has a single implementation with some CPUs and GPUs under it. That's absolutely like a huge part of what Anari is going for. But there are these others that when you have a standard semantic capture of what the scene is, and then how to, or the desire to get frames back from a certain vantage point of that scene, you can do interesting things like an implementation can farm off even subparts of the same image to multiple nodes in like an MPI cluster, or the far right side, you could have an existing distributed memory application, like an MPI simulation, where bits of the scene are on different nodes and they all talk to the same Anari API, and then the underlying implementation can take that and make a single image of all of the data. These are things that we've been doing in SciViz for a while now, but being able to lower the bar to be able to access those renderers is something that we're keeping in mind as we're working on Anari. So the current status is we've been a working group for just a couple of months now. It's very early on, but we've got some really cool examples already. We have an early first light of VTK with some of its infrastructure for rendering. VTK, for those of you that don't know, is the visualization toolkit. It is a very ubiquitous package from Kitware to deal with filtering and then rendering of scientific data or simulation data. And we have the first light of it, given that it was part of the participating reason and cause for Anari to start as an effort. And then also VMD is a visualization package for molecular dynamics, VMD. And both of those have been early adopters to help drive some of the changes or the design decisions we're making at Anari. And we have a number of implementers as well, which has been very exciting. We're still exploring lots of possibilities. We from a technical perspective, we're trying to write the software first and then write the spec, because talking about a spec outside of what we're going to do in practice is really difficult to keep the discussion focused. So what we did is we took the Osprey API and we have taken it and started working with that as like a concrete starting point. And there's a number of good changes that we've been working on there to make sure it best fits all of those execution topologies, different renderers, different shading models, different volume types, surface types. All of these things are properly handled, but we're making a lot of exciting progress there. And so this showcases not that we're all trying to implement the same renderer, but rather VMD has all this scene loaded in memory, ready to go, and was able to hand it to the Anari API. And just by virtue of selecting what backend Anari was being used, we could get a great image from a GL implementation that NVIDIA is working on called NVGL Osprey. NRX is an optics-based implementation that NVIDIA was working with. And then, of course, the far right is all of the code that was handwritten inside of VMD, what it's looking like. And we even have efforts from John Stone, who leads the VMD effort, to work on his rendering code also be in terms of the Anari API. So then there's so much code that can get removed from VMD to dispatch to these different rendering packages without having to re-implement them. So it's an exciting gamut of possibilities, and this is just a first light. But all of that being said, I just wanted to whet your appetite with some things that when you commoditize how you talk to a rendering system, we're not trying to standardize on necessarily the limits of what is the perfect material model, what is the perfect lighting model. What we're trying to do is say, if you have like OSL or Material X, or you have a bunch of like the Disney principled BRDF shaders in your renderer, that we want to standardize the way you express that to your live system and then encode that to the renderer, instead of saying like there's only one answer and everyone should use that. Still a good discussion, but not, it's outside of the scope of what we're doing. Meaning with the principled BRDF and car paint shaders and Osprey, Anari can make images like this, or make images like this, where we combine volume rendering and surfaces together. The API lets us still express all kinds of details that we find in professional content creation. So I guess the call to participation here is that Anari is, yes, emerging from scientific visualization, but absolutely something that could be very relevant and useful in the professional rendering space as well. We have a lot of people participating. It's been exciting to see lots of people want to get on board with helping craft what Anari is starting to look like. But we are absolutely looking for as many people to want to come participate as possible. And so we are a working group. We do now have an email list, an email address that you can send questions to if you're not a participating workgroup member. And of course, the feedback is always welcome. Things that you would like to see in something like Anari, and then of course we would love it if you come participate in the working group itself. We have lots of ideas and would love to know if they're relevant, and of course your ideas that you have that we haven't thought of. And with that, I'll turn it back to, I guess, Sean.
Thanks, Joe. That's great.
No, unfortunately, we can't hear you, Sean.
Can you hear me now?
A little bit.
Well, that's great. Thank you very much. If you have any questions, please feel free to use the question and answer box here. Or if I think we only have a couple minutes left, but if you're watching this recorded later, please feel free to go on GitHub for any of these projects and to engage with the mailing lists. Everybody on this team is very
Sean, I think we lost you again, but maybe I can facilitate the Q&A. So we do have our first question that is, does OpenVKL have support for motion blurred volumes? And Greg, and we have Johannes Meng as well, I guess could take that.
Yes, so today OpenVKL does not currently support motion blur volumes through our API. This is something we are looking into. I would say if you have specific needs regarding motion blur on specific volume types and so forth, feel free to reach out to us via GitHub and so forth, and that'll help us prioritize our development.
Great. Do we have any other questions from the audience while we're on the line? Yeah, so looks like we're getting close to the end today, and I don't know if there's any other questions that that may be out there. We do have GitHub is where you can find all of our projects, and always feel free to reach out to us there with specific concerns about each project. Probably using GitHub issues. You can also find mailing lists as well associated with those projects to contact us, and we'd love to hear from you about things you're interested in, things you're doing with our projects, or things that our projects aren't yet doing that are interested to you. Cool. We do have a question. Will the charts here in this seminar be available? And it is being recorded, and so this talk will be up on YouTube. And I'm not sure about the slides themselves, but you can at least see this talk again up on YouTube after today. Okay. Thanks, everyone. We appreciate your attention, being with us, and hope to see you in the future. Have a good one. See ya.